Good day everyone, and welcome to day 29 of our 30-day structure analysis challenge. Thank you so much for staying with us this far. So today we want to conclude our design on the slab we started designing 2 days ago, and today we want to do something called deflection check. We want to check if all these parameters that we provided are okay, right, if they will pass. Now, deflection check is the measure or the comparison between actual deflection, which is the effective span over effective depth, with allowable deflection, which is basic span ratio multiplied by modification factor. Now, for a simply supported slab, which is the case that we are handling, your basic span ratio is 20. Now, these things are provided for you in your BS code, so you need to pick up your code and study them. So your basic span ratio is 20. Then your L over D is the length we are working with, 4650 divided by 119. We have already discussed how we got this value, and this is what you get, 39.08. So your modification factor is this expression you can see right here. Now these formulas are also in your code, so you don't have to cram them. So your modification factor is this representation, 0.55 plus everything we have here. Now this particular expression Fs is obtained by this formula. This formula is also in your code. So this is 2 multiplied by strength of steel multiplied by AS required all over 3 multiplied by AS provided multiplied by 1 over beta B. Now when I plug in my values, beta B is represented as 1 for this scenario that we are working with, so I do not have to write it because it's essentially 1 over 1. So when I compute this, I have 296.92. I simply take this and I fix it back into this formula. We know what m over bd squared is. This is your maximum moment all over your breadth, which is 1000 by the same d effective depth, 119 squared. So by the time I have all of this in the formula and I compute, I get this expression 1.17, right? So all I have to now do is rewrite this and see if this statement is true. This is 39.08. Is it less than 20 multiplied by 1.17? And this is 39.08, and computing this we have 23.4, which is obviously not greater than 39.08. This means that our provisions are not okay. They are not okay. Now, don't weep. Design is, I won't say design is trial and error, but design is subject to errors. So it is your job to fix these errors when you encounter them. So what can we do to actually fix this error? You find out that our effective depth is a function of the overall depth minus the concrete cover minus half of our reinforcement diameter. If we increase this overall slab depth, you find out that this number increases, and if this number increases, essentially this number reduces. That's what it means. So increasing this number even goes ahead to reduce this number, right, which in the long run increases this number. So there are a lot of English flying around here, but then essentially when you have a failure like this, the first thing you want to do while you are redesigning is to increase the overall thickness of your slab. Increasing the overall thickness of your slab will increase your chances of passing deflection. You can also increase other factors like your rod, but then most at times we want to use the same 12mm rod, because using higher rods will make the slab too heavy. So the safest bet is increasing the thickness of your slab. Playing around with the parameters like that has a way of balancing everything out, so at the end you will obtain a result that will actually pass this deflection check. So you keep trying and you keep doing it till you get it right. That is design, that is engineering, and that is what we are here to do. So thank you very much for staying with us through to the end of this video. Continue to like, continue to follow, continue to comment, as we have taken and we are still taking structural and civil engineering concepts one step at a time, making them easier for all of us to understand. Thank you.